start with a simple thought. Have you ever noticed how a swing moves back and forth? How sound travels through air? Or even ang pagtibok ng puso mo? These everyday motions might seem ordinary, but they all share a beautiful rhythm. That rhythm is the language of oscillations and waves. An oscillation happens whenever something moves repeatedly around a central point, like a pendulum swinging or even your lungs as you breathe in and out. It's motion that goes there and back again. In every oscillation, there's a balance between two forces, one that pulls the object away from equilibrium and another that brings it back. The result, motion that repeats itself in time. Now, when these oscillations don't just stay in one place, but actually travel through a medium, carrying energy from one point to another, that's when they become waves. So, if oscillation is motion, a wave is motion that moves the energy. Just like in waves, the swing's motion shows how energy moves in a repeating pattern without the object permanently changing its position. So, every time we ride a swing, we're actually experiencing oscillation and wave motion in real life. Physics gives us the language to describe that motion, but curiosity gives it meaning. Because once you see the world through oscillation, you'll realize nothing ever truly stands still. Everything vibrates, connects, and resonates.
We define this motion using two terms. The period is the time for one complete cycle. The frequency is the number of cycles per unit of time. Frequency and period are reciprocals. The unit for frequency is the hertz, which is 1 cycle per second. Let's try the example. If a pendulum completes 30 cycles in 15 seconds, what is its frequency and period? Frequency is cycle divided by time. 30 divided by 15 seconds give us a frequency of 2.0 Hz. The period is the reciprocal of the frequency. 1 divided by 2.0 Hz give us 0.50 seconds. That's how long it takes for one complete swing.
So now, let's talk about simple harmonic motion, or HSM for short. It is one of the most common types of periodic motion that we see in everyday life. Objects that move back and forth over the same path, like a swinging pendulum, a bobbing metal weight, or a vibrating guitar string, all show what we call periodic motion. But there is one special kind of periodic motion. It is called simple harmonic motion. It happens when an object moves back and forth from a central position. Because of our restoring force, that is a force that always pulls it back toward the center of the equilibrium position. In simple harmonic motion, we can describe the motion using displacement, velocity, and acceleration. The displacement is how far the object is from the equilibrium position. The maximum displacement on either side is called the amplitude, or the variable A. The number of vibrations per second is the frequency, and the time for the one complete vibration is the period, or the variable T.
So now, I will be explaining the equations for simple harmonic motion, or SHM, which describe how an object moves when it vibrates or oscillates, like a spring or a pendulum. So first is the period of the spring. The first equation is T is equals to 2 pi times the square root of m over k. So this formula gives us the variable T, the period, or the time it takes for the spring to complete one full vibration. Here, m stands for the mass of the object in grams or kilograms, and k is the spring constant in dynes per centimeter or newtons per meter, which measures how stiff the spring is. So if the mass increases, the period also increases, meaning the spring moves slower. So in the next equation is the maximum acceleration, or the A sub max, equals negative 4 pi squared A over T squared. So this gives the maximum acceleration of the object, the greatest speed change it experiences while moving. The variable A means amplitude, or how far the object moves from the center. The negative sign tells us that the acceleration is always directed back toward the center and not away from it. So the third equation is the acceleration from the equilibrium position. So the last equation is A is equals to negative 4 pi squared x over T squared. So this tells us the acceleration at any point in the motion when the object is a distance x away from the equilibrium position. Again, the negative sign means the acceleration pulls the object back toward the center. That's why it keeps oscillating. So in summary, the first equation tells us how long one oscillation takes. The second shows the fastest acceleration. And the third shows the acceleration at any position. These equations together describe how an object moves in simple harmonic motion. Smooth, repetitive, and always balanced by a restoring force.
Example problem. So now, let's apply this equation in an example. A 100-gram body is attached to a spring with a spring constant of 2000 dynes per centimeter. It is displaced 10 centimeter from its equilibrium position and release. Now, we are asked to find the variable t or the period, the maximum acceleration or the a sub max, and the acceleration when x is equals to 5.0 centimeter. So these are the given data. M is equals to 100 grams, K or the spring constant is equals to 2000 dynes per centimeter, A is equals to 10 centimeter, and X is equals to 5.0 centimeter. So when finding the period T, we use the formula T is equals to 2 pi times the square root of M over K. So just substitute the given value in the equations, and after solving, we get T is equals to 1.40 seconds. Therefore, the object completes one full vibration every 1.4 seconds. So now, after finding the period of the spring, we will move to the maximum acceleration. So we will use the equation A sub max is equals to negative 4 pi squared A over T squared. So just substitute the values, and we will get the value of negative 200.3 centimeter per squared. So the maximum acceleration of the body is negative 200.3 centimeter per squared because it acts towards the equilibrium. So now, after finding the period of the spring, we will move to the maximum acceleration. So we will use the equation A sub max is equals to negative 4 pi squared A over T squared. So just substitute the values, and we will get the value of negative 200.3 centimeter per squared. So the maximum acceleration of the body is negative 200.3 centimeter per squared because it acts towards the equilibrium. For the last one, finding the acceleration at x is equals to 5.0 centimeter. So we'll just use the equation of acceleration from any position, which is the a is equals to negative 4 pi squared x over t squared. So just substitute all the given values, and we get the answer of negative 100 centimeter per second squared. Therefore, when the body is 5 centimeter away from its equilibrium, its acceleration is 100 centimeter per second squared towards the center. So in conclusion, simple harmonic motion is a periodic motion where the restoring force is proportional to displacement. The key equations help us find the period, amplitude, and acceleration. By using the formulas, we found that the value of the t or the period is 1.40 seconds. The value of the a sub max is negative 200.3 centimeter per second squared. And the value of the acceleration is negative 100 centimeter per second squared.
Let's move on to another topic. Ever watch a spring bounce and gotten lost in its rhythm? That perfectly predictable back and forth motion is called simple harmonic motion. And our star today is spring mass oscillator. This system, a mass attached to a spring, is one of physics' most fundamental models. Its rhythm, controlled by two things, the mass and the spring stiffness, known as the spring constant. To understand this, imagine a trampoline. The weight of a person and the tightness of the spring are what decide how quickly they bounce up and down. It doesn't matter if they take a big jump or a small hop. the speed of the bounce itself stays the same. We quantify this rhythm using three interconnected concepts. The most important is the period, the time it takes for one full cycle. It's governed by this formula. T equals 2 pi times the square root of m divided by k. The other two are just different ways to measure the same beat. Frequency, which is spelled capital F, tells us the number of cycles per second. It is the inverse of the period. The formula is F equals 1 divided by T. We measure frequency in hertz, spelled Hz. And angular velocity, symbolized by the lowercase Greek letter omega, tells us the rational speed of the motion. The formula is omega equals 2 pi times f. We measure angular velocity in radians per second, or rad/s. Let's put this rhythm to the test with a classic example. Suppose we have a spring with a stiffness K equals 300 newtons per meter and a mass of m equals 0.75 kilograms. We'll find all three: the period, frequency, and angular velocity. Watch how quickly we uncover this natural beat. First, the period. Plugging our values into the formula. T equals 2 pi times the square root of 0.75 divided by 300. That square root simplifies to 0.05. Multiply that by 2 pi and we get T is approximately 0.3142 for one complete cycle. Fast, no? Next, the frequency. Kini, simple ra kaayo. It's just the reciprocal of TF equals 1 divided by 0.3142, which is approximately 3.183 Hertz. This means the mass completes more than 3 full cycles every single second. Finally, the angular velocity. We use the formula omega equals 2 pi f. We substitute the constant in our calculated frequency. That gives us omega equals 2 times 3.14159 times 3.183 Hertz. First, we multiply 2 by pi. 2 times 14,159 equals 6.283. Now, we multiply that result, 6.283, by the frequency of 3.183 Hz. Our final result is 19.99 radians per second, which we round up to the clean 20 radians per second. And there you have it! The spring mass oscillator is a perfect, predictable engine governed by only its mass and stiffness.
So now let's go through simple pendulum and physical pendulum. Pendulum are important in physics because they help us understand oscillating motion, that back and forth and swinging movement that occurs under the influence of gravity. A simple pendulum. A simple pendulum consists of a small heavy object called bob, suspended by a light and extensible string fixed at one end. When displaced from its equilibrium position and released, the pendulum swings back and forth in the force of the gravity. Physical pendulum. A physical pendulum is any rigid body that oscillates about a pivot point, rather than a small bob on a string. For example, it includes a swinging baseball bat or a door oscillating on its hinges.
And now, let's go to the equation of a simple pendulum. The time period t, which is the time it takes for one complete swing, is given by the equation t is equals to 2 pi times the square root of L over G, where t is the period in seconds, L is the length of the pendulum in meters, G is the acceleration due to the gravity, or meter per second squared, and the last one is the 2 pi and has a constant value of 6.28. So we'll just remember that the mass of the bob does not affect the period. The amplitude for small angles does not affect the period. The gravitational field strength and the length of the pendulum determine its time period. So we have an example problem here. The given are the L, which is the length with 1.0 meter, T or the period with 2.0 seconds, and it is required to find the value of G at the point of the pendulum, and find the new period of T when G is equals to 9.85 meter per second squared. So in solution for finding the G, start with the formula T is equals to 2 pi times square root of L over G. So we just square both sides to eliminate the square root. We will have T squared is equals to 4 pi squared L over G. And then rearrange for G, we will have the new formula, which is the G is equals to 4 pi squared L over T squared. Now just substitute the known values. For pi, 3.14, for the L or length, 1.0, and the T, 2.0. So just compute step by step. Now we will have an answer of G is equals to 9.87 meter per second squared. So in solution for finding the new period or the T, just use the same formula. T is equals to 2 pi times the square root of L over G. So just substitute the given values. T is equals to 2 pi times the square root of 1.0 over 9.85. So compute. T is equals to 2 pi times 0.3187. So we will have an answer of T is equals to 2.0 seconds. So we will go to the equation of a physical pendulum, which is the T pi times the square root of I over mgl, where I is the moment of inertia about the pivot, m is the mass of the body, g is the acceleration due to gravity, and L is the distance from pivot to center of gravity. But if I is equals to mt squared, where k is the radius of the gyration, then T is equals to 2 pi times the square root of k squared over gl. So we have an example problem here. Given distance from pivot to the center of gravity, L or length 1.0 cm to 0.01 meter. Radius gyration, K is equals to 60 cm to 0.60 meter. Required, find the period T of the body. So in solution, we will just use the formula T is equals to 2 pi times the square root of K squared over GL. And now, just substitute the given values. K is 0.60, G is 9.8, and L is 0.01. And just compute step by step, we will have an answer of T is equals to 12.05 seconds. Note that the page shows T is equals to 1.5 seconds, which suggests as a possible typo. If we solve backward, the correct radius of gyration that matches T is equals to 1.5 seconds or 7.5 centimeter would be around K is equals to 0.075 meter. In conclusion, simple pendulum has a formula of T is equals to 2 pi times the square root of L over G. The period increases with length and decreases with stronger gravity. Mass and amplitude do not affect the period. In physical pendulum, it has a formula of T is equals to 2 pi times the square root of I over mgl, or 2 pi times the square root of K squared over gl. And it also depends on the body distribution of the mass or the inertia.
What is underdamped motion? It's the movement of an oscillating system where the damping force is weak enough to allow the object to complete several full swings before coming to rest. Look at the graph. The line is a classic decaying wave. The system oscillates, meaning it repeatedly crosses the equilibrium point. But the amplitude of each swing gets progressively smaller. It's a gradual settling. This happens because the force trying to stop the motion, the damping force, is weaker than the force making it oscillate. The object has enough energy to overcome the resistance multiple times before its energy is fully dissipated. A common example is a good car shock absorber. It absorbs a bump and lets the car bounce just a couple of times before settling, ensuring a smooth, controlled stop to the vibration.
Basically, overdump motion happens when some time goes back to its original position slowly and doesn't bounce or oscillate. In short, it moves back to rest pero super hinay kahit too much dumping force. Like sobrang lakas raw ang resistance. Like this. Diba, when you close it, dili siya mo bangka or dili siya mo sweep pabalik diri na. So it just slowly shut down and very smooth and chill.
Start.
So in physics term, overdump means the system has too much dumping. So instead of vibrating or oscillating, it just slowly returns to its balance point. Kaya kung gamay na ang dumping, mo-oscillate pa siya. Pero kung sobra, hinay na kaayo. Mao na siya ang ginatawag na overdump motion. This kind of motion is important in real life kaya it keeps things stable and controlled, like in machine or door. We don't want them to vibrate or shake too much, so engineers actually design some system to be overdump for a smooth movement. So to summarize, overdump motion means too much dumping, so the object goes back to rest slowly but steady. No bounce, no oscillation, just chill and smooth.
Did you know that critically damped motion lets a system return to rest quickly without oscillating? A system is said to be critically damped when it returns to its original position as quickly as possible without overshooting or bouncing back. In other words, it moved back to its balance point smoothly, no extra motion or vibration. In physics, critically damped motion means the damping is perfectly balanced, not too weak and not too strong. Kung kulang ang damping, mag-oscillate pa siya. That's underdump. Kung sobra, hinay kaayo mo balik. That's overdump. Pero kung sakto lang, that's critically damped. Smooth, fast, and no oscillations.
This kind of motion is important in engineering and mechanics, like in doors, window system, or vehicle suspensions. It helps make movement faster but stable, preventing unwanted shaking or delay. In short, it keeps the system efficient, safe, and reliable. To summarize, critically damped motion means the system returns to rest as fast as possible, without bouncing or overshooting. It's the perfect balance. Not too fast, not too slow, just right.
Now, mag-dive ta sa fundamental words sa physics para mag-explore sa mechanical waves. Moni ang disturbance nga gadala sa energy through matter or space. What is mechanical wave? It is the disturbance that transfer energy through matter. The key word is medium, like air, water, or a solid. Mechanical wave need a medium to travel. Quick check on wave parts. The high point is the crest, and the low point is the trough. The height is the amplitude, a measure of the wave's energy. Now, for the two main types defined by how medium's particles move relative to the energy. First, the transverse wave. Imagine shaking a rope up and down. The energy moves forward, but the rope particles move perpendicular, up and down, at a 90-degree angle to the direction of energy flow. Water waves and waves on a guitar string are classic transverse example. They create those familiar crests and troughs. Next, the longitudinal wave. This time, the particles move parallel to the energy. This parallel motion creates two regions: compression, where the coils are squeezed together, and rarefaction, where they are spread apart. The most important example, sound. Sound waves are simply compressions and rarefaction traveling through the air. The energy travels across the room, but the air molecules just move a little bit back and forth in the same direction. So, remember, transverse is perpendicular motion and longitudinal is parallel motion. Mechanical waves are everywhere.
Did you know that periodic waves repeat their pattern over time, just like sound or light waves? A periodic wave is a type of wave that repeats its pattern continuously over time, forming a regular cycle just like smooth sine wave. It moves up and down in a steady, consistent rhythm. For example, think of the waves sa dagat. They rise and fall repeatedly in a continuous motion. Or imagine sound waves. Every time we speak or play music, the vibration travels in a repeating pattern through the air. Even radio or Wi-Fi signals follow periodic wave patterns. The length of one whole wave cycle, amplitude, the height or strength of the wave, period, how long it takes for one whole wave to pass, then frequency, how many waves pass in 1 second, velocity, speed, how fast the wave travels. These parameters help us understand how waves move and very important because they explain how energy travels, like in sound, light, and even earthquake waves. They help engineers and scientists develop communication systems, radios, and earthquake-resistant structures. Almost everything that moves in a rhythm or patterns can be explained through periodic waves.
A sinusoidal wave or sine wave is the most perfect example for oscillation in motion. It's smooth, continuous, and predictable, a shape that repeats over time, representing how energy moves through space in a rhythmic way. Have you ever wondered why so many things in nature move so smoothly? From the gentle sway of a tree branch to the vibration of your phone, there's one hidden pattern behind it all. The sinusoidal wave, the purest and most fundamental form of periodic motion. What's amazing is that even the most complex rhythm in nature, the rustle of leaves, the crush of ocean waves, or the hum of the wind, can all be traced back to the same simple pattern, the sine wave. It's as if the universe itself moves to a single timeless beat, smooth, continuous, and perfectly in tune. What's amazing is that even the most complex rhythm in nature, the rustle of leaves, the crush of ocean waves, or the hum of the wind, can all be traced back to the same simple pattern, the sine wave. It's as if the universe itself moves to a single, timeless beat, smooth, continuous, and perfectly in tune.